Continuing with test number 2 solutions, we're up to problem number 12. A worker pulls a 75.0 kilogram crate across a surface with a force of 220 newtons directed at an angle of 40.0 degrees above the horizontal. He pulls for 2.50 meters. Let's draw a picture. So here's the crate pulling on the surface, and here's the either it's a rope or actually the worker's arm, but pulling, but it's at an angle. It's not directly in the motion, horizontally in the direction that the crate's going to move. The force is going upward. So how much work does the worker do on the crate? So work is force across a distance. It's force times distance. We have the distance, so we just have to multiply by the force. However, we have to remember that you only use the component of force in the direction of motion. So the force is going like this. It's 220 newtons, but only a component of it is actually pulling in the direction of the motion. So this is F, this will be F, and that's going to be cosine theta, right? That's the adjacent side. So the work is going to be force times cosine theta, and then times the amount that it moves by. Okay, so it's going to be 220 newtons times the cosine of 40 degrees times 2.50 meters. And that comes out to be 421 joules. So the worker does 421 joules of work on the crate. Remember, work is a transfer of energy. So that's 421 joules of mechanical energy going into the crate. Question B on this problem was, how much work does gravity do from the Earth? Gravity from the Earth do on the crate? So, of course, gravity is going this way. It is perpendicular to the way the crate is moving. It has zero component in the direction that the crate is moving. So it's going to do 0 joules of work. It's not adding or subtracting any mechanical energy from the crate. Okay. So C is, suppose the crate was initially at rest, and at the end, after it's gone this 2.50 meters, it's moving with a speed of 1.20 meters per second, right? Because we're pulling it, so now it's going that fast. So the question is, how much mechanical energy must have been lost? And the key word here is lost. A lot of people, I guess, miss that word. So here's the thing. It was initially at rest, so it had initially 0 joules of mechanical energy. We can figure out how much energy it has at the end. 1/2 mvf squared. So we put in the numbers like that, and that comes out to 54.0 joules. So it went from 0 joules to 54.0 joules. So it went up by 54 joules. Now, where did that energy come from? That energy came from the work that was done. Right? That's how the object got its speed, and kinetic energy is based on speed because of the force. So, but 421 joules though were added. So 421 joules were added, but it only kind of like kept 54 joules. Only 54 joules is showing up in terms of how fast it's moving. So the rest of that energy that was put in through work apparently was lost. Does that make sense? So again, 421 joules went in. We poured 421 joules into this crate, but it's only keeping 54 joules of it by the end. So we have to subtract the two. So the 421 joules minus the 54 joules is 367 joules was lost. That's how much was lost, and that would have just been, again, through that energy. Instead of being kept as kinetic, it went into internal energy. We know it didn't go into potential energy because there's no springs involved, and it didn't go up or down, so there's no gravitational potential energy. So no potential energy is being employed here. So if it didn't go into kinetic energy, it must have been lost in terms of internal energy. So the crate heated up, the floor heated up, sound was emitted, and all that. Okay. Next problem, number 13. A 60-kilogram archer is standing on frictionless ice. He fires a 0.50 kilogram arrow horizontally to the right at a speed of 45 meters per second. Does the archer move? If so, in which direction and what is his speed? He's on ice, so there's no friction. So we have two objects: the system of the archer and the archer and the bow, and the arrow. Think of the archer and the bow together, and the arrow as our system. And initially, this system is at rest. And now he fires it, right? So now, this system is an isolated system. Horizontally speaking, there are no external forces. The forces are just between the archer and the bow and the arrow, which is internal to this system. All right. So afterward, the arrow is going this way, and we know how fast. In an isolated system, momentum must be conserved. This is a conservation of momentum problem. So the momentum in this picture has to equal the momentum in this picture. So since the momentum here is clearly zero, nothing's moving, then the momentum in this picture has to add up to zero. But the arrow has positive momentum going this way, therefore the archer has to have negative momentum going this way. And it's the recoil. We talked about that. If you fire a gun, if you throw anything, there's going to be recoil, and it's going to push you back. If you're the one throwing or shooting or firing, you're going to get pushed back. Now, usually if there's friction, you don't move because of the friction. That means you're not an isolated system, because friction from the surface is an external force. But here we've removed that because we're on frictionless ice, so there is no way for the archer to stay still. There is nothing to counteract the pushing back force, the recoil force. And so the archer will in fact go backward. And we can figure out how fast. So as we've already set this up, we've got zero momentum in the beginning. So that is what the total momentum at the end has to be. That'll consist of the momentum of the archer times the velocity of the archer plus the mass of the arrow times the velocity of the arrow. These two have to add up to zero. This one's going to be positive, this one's going to be negative. All right, so you solve for velocity of archer, right? That's what we want. So you bring this term over. So you do some algebra. Okay, divide. So the velocity of the archer is the mass of the arrow times the velocity of the arrow divided by the mass of the archer. Okay, we put in the numbers, which looks like that. I'm putting in a positive 45 meters per second for the velocity of the arrow because it's going to the right, which is the positive side. I am sorry, I've got a negative sign, the all-important negative sign. When I moved the mass of the arrow times the velocity of the arrow term to the other side, I was subtracting, so that's negative, that's negative. Okay, because I'm definitely expecting a negative answer here. And I get negative 0.38 meters per second. So that means the archer will be going 0.38 meters per second to the left because of the recoil and because of conservation of momentum specifically. Okay. Okay, I still have two problems to do, so maybe I'll do one more video. I'll separate it out. And so one last video with numbers 14 and 15 coming up.